We now want to talk about Newton's Universal Law of Gravitation. And the Universal Law of Gravitation is given by this equation right here. F equals capital G m1 m2 over r squared. Now there's a lot to unpack with this equation, and we really aren't going to go into the history of how the equation is derived. Okay, we're just going to hand it to you for now. But first, preliminary considerations, let's notice a few things. Okay, so first of all, we have this G, this capital G. This is called Newton's universal constant, universal gravitational constant, okay? And it's just a constant of proportionality inside the equation, but it does have a very specific value, okay? And that value is 6.67 times 10 to the negative 11 newtons times meters squared per kilogram squared in the SI system, okay? And this is a very, very important constant, as we will see down the road. The second thing to notice is that the gravitational force between two objects is proportional to the product of their masses. And if you think about it, that makes sense. The more massive the objects are, the more gravity should be affecting each other. And that makes some intuitive sense. And lastly, the force is proportional to the inverse of the distance between them squared. Okay, so here R is the distance between the two masses. So if I look at a situation like this where I have two objects, and R is the distance between their centers. Okay, R is the distance between their centers. As your textbook explains, technically the force law is applicable to point masses, objects with zero size, or perfectly spherical objects. But most things in physics, particularly where we apply the universal law of gravitation in astronomy, things like stars, planets, are roughly spherical. Or the law will hold if you have a non-spherical object orbiting another object, but their distances are very, very large. The distances between them are very, very large compared to their sizes. So that's why things like Mars moons that aren't quite spherical, you can still apply the universal law of gravity there because they're far enough away that their non-sphericity is not really playing a gigantic role in the gravitational force they feel from Mars. Okay. Now, this is known as the inverse square law, or one instance of an inverse square law. And inverse square laws are extremely important in physics. We're going to run into another one when we start to study electricity. Okay, and it's not necessarily intuitive that the force had to be proportional to the inverse of the square, but it should make sense that it is in some way proportional to the inverse of the distance. In other words, the closer and closer I bring these two masses together, obviously the more gravity should affect them. The further and further I pull the masses out, the less gravity should affect them. So it should be proportional to the inverse of the distance in some way. It just so happens that it's actually inversely proportional to the square of the distance. Okay? So in the next video, we will actually talk about some of the consequences of the inverse square law, how to use the inverse square law, and then we will also see a pretty interesting consequence as applied, consequence of this equation as applied to the Earth. All right, we'll see you then.